Hello friends, good morning and welcome back to my YouTube channel Bedanta Kr Camps and Vlogs. So in the last lecture I was discussing about green chemistry, and today's also my topic will be green chemistry lecture 2. In the first lecture, which is uploaded in the YouTube, and probably you have seen this lecture, and there I try to explain what was the need for green chemistry, why people tried to modify chemistry with a term including green chemistry. So at that time, famous chemical industry, they have to change their company slogan, better living through better things from chemistry to better living through better things from science. Because the people were upset and they tried to blame the chemists and the chemical industries of poisoning this planet or triggering environmental disaster. The series of events that took place, that is the burning of the Koyego River, smog in Tokyo, mercury poisoning in Japan, thalidomide tragedy, the blast in the nuclear reactor Chernobyl, and of course the deadly Bhopal tragedy in 1984 due to leakage of the poisonous methyl isocyanate gas. So people started pointing finger to the chemists and the chemical industries that they are the source of contamination of this planet. And in 1962, Russell Carlson, the famous book Silent Spring, it catalyzed the environmental movement which was taking place globally. So in the 1990s, Paul Anastas, he forwarded 12 principles of green chemistry, and with this 12 principles, our chemistry may be environment friendly. The main goal of green chemistry is to reduce the risk of carrying chemistry in this planet by utilizing a set of 12 principles which we call the 12 principles of green chemistry. So in the principle 1, they are saying about prevention of waste, and in the principle 2, they are saying about atom economy, and I will say that both principles, that is principle 1 and principle 2, prevention of waste and atom economy, are the either sides of a coin. So many people ask me, sir, what books you are following? Actually, I follow a lot of books. I also visit the internet. But for the BSc student, I think this book is very good. That is New Tense Green Chemistry by V.K. Alwar and M. Kidwai. It is available in Amazon and it is available in Flipkart also. So this book is a little bit costly nowadays. So there is another copy, the second copy of this book. Actually, I forgot the name. So if you just go through Amazon, they will find the textbook upon green chemistry by V.K. Aluwalia and M.K. Kidwai, and that will be a better book for the BSc students and for the MSc students. So, in today's lecture 2 on green chemistry, I will again give you a presentation, and there I will be basically touching the first 2 principles, and I hope you'll be able to accumulate the ideas of green chemistry. And please keep watching my channel, and in the coming days I will be uploading more such videos which will be directly benefiting the BSc students. And if you really like it and love it, you do not forget to subscribe my channel Bedanta Kr Camps and Vlogs. So here we go for my presentation in PowerPoint. So here we go for the presentation. Green chemistry, new phase of chemical sciences, and myself Bedanta Kr Borah, Associate Professor, Department of Chemistry, Debraj Roy College, Golaghat, Assam. So you can email me bedanto69@gmail.com, or you can also call me at 985-999-2020, of course, India code +91. So this is the second lecture upon green chemistry. So as I've already told you, that I'll be discussing here the first 2 principles out of the 12 principles of green chemistry. So here are the 12 principles of green chemistry: prevention, atom economy, using less hazardous
chemical synthesis, designing safer chemicals, safer solvent and auxiliaries, design for energy efficiency, use of renewable feedstock, reduce derivatives, catalyst, design for degradation, real-time analysis for pollution prevention, enhanced safer chemistry for accident prevention. So as new generation chemists, they'll be trying to, or they'll be developing new processes, and these processes could be called as green process if they can logically, the process can be supported by either of these 12 principles. So the first prevention principle, it is about prevention. It is better to prevent waste than to treat or clean up waste after it is formed. Okay, so our chemical process must be clean so it does not generate waste. We do not like to have such type of chemical process where a chemical reaction generates a lot of waste. So the green chemistry suggests that your chemical process must be so that waste generation can be minimized. So here I am giving you an example of ibuprofen. You have already heard about ibuprofen. It is an analgesic, anti-inflammatory agent, which is used to reduce the swelling and of course reduce the pain. So this is the structure of ibuprofen. This is the structure of ibuprofen. This is your ibuprofen. Now here you can see how you are producing ibuprofen. This is your ibuprofen. This is the classical method, and it synthesizes ibuprofen from this starting material from by 1, 2, 3, 4, 5, 6 steps. So these are the 6 steps, and more number of steps means what? You will be using more auxiliary substances like solvent, etc. Then there will be more energy need. So, and also as the number of steps increases, the waste generation will increase. So here there is only 40% atom economy. That means out of the total reactants which you are using, 40% of the atoms are only present in the product, and the remaining 60% is waste. So this is the BHE company synthesis of ibuprofen in 1992. From 6 steps, they have reduced to only 3 steps. They're using the same starting material. Here you can see this is the starting material in the BHE synthesis of ibuprofen, and this is the brown synthesis of ibuprofen. They're using the same starting material, but the classical synthesis involves 6 steps, whereas the green synthesis, which you can say, it involves only 3 steps, and the atomic economy is 77%. Now let us try to understand what is happening in each of these steps. What type of waste is getting generated? So this is the classical route for ibuprofen synthesis. So in the first step, you are carrying acylation. So this is, you are putting the acyl group in the para position, and you are using acetic anhydride with aluminum chloride as catalyst. And in this process, the waste generated is hydrochloric acid, acetic acid, and of course, aluminum waste. So here all the red alphabets, they are the waste which we do not like to generate during a chemical synthesis. So in the first step, you are releasing acid to the environment as well as aluminum waste. The second step, they are using ethyl chloroacetate, that is a Darjan glacidic ester condensation. You are using sodium ethoxide, and in this process again hydrochloric acid is generated as a waste. Third step, hydrolysis. You are hydrolyzing it, again you are generating acetic acid as waste. So here you can see in all the first 3 steps, you are releasing acid to the environment in the form of waste. So as the number of steps increases, the quantity of reactant increases, and the atom economy decreases, and the environmental E factor is also increasing. So I will be just shortly discussing what is the atom economy and what is the E factor for environment factor for a green synthesis. So as the number of steps increases, waste generation is also increasing. So you are all releasing acid, and in this step you are releasing ammonia to the atmosphere, and these materials are not at all economy environment friendly. So it is also hurting the environment, and also there is an economic loss because more steps, more raw material you are putting it in the process. So this is the West route to ibuprofen synthesis. Here you can see out of 6 steps in the classical synthesis, the Brown synthesis, the same using the same starting material, you are using preparing ibuprofen, and the number of steps has been reduced to only how much? Only 3 steps. And here the only waste that is getting generated in the first step, that is acetic acid. And in the classical synthesis, here you see all this red danger, they are waste, they are acid waste, they are base waste getting released to the environment. But the West synthesis of ibuprofen, they are reducing the synthesis from 6 steps to only 3 steps. And the only waste that is getting generated is only in the first step, that is acid. So by the West route, we can call it as the green route because this route is generating less number of waste, and as a result, the atom economy is increasing from 40% to 77%. In the classical synthesis of ibuprofen, that is the Brown synthesis, the atom economy was only 40%, whereas the West synthesis for ibuprofen, which they are synthesizing ibuprofen only in 3 steps, the atom economy is rising significantly to 77%. So the first principle of green chemistry works. The first principle of green chemistry is suggesting to develop process where minimum waste is generated. So economic advantage of BSC synthesis of ibuprofen: greater throughput and overall yield, 3 step versus 5, greater atom economy, few auxiliary substance, because as the number of steps get reduced, the use of auxiliary substance also get reduced. Auxiliary substance includes the solvents, catalyst, etc., derivatization, etc. So again, this is the green synthesis of another example where you are applying principle 1 to find a green process. This is the synthesis of MIC, means methyl isocyanate. And this was the gas which was responsible for the Bhopal gas tragedy in 1984. So this is the green synthesis. They are using methanamine and they are treating with carbon dioxide, and they are using some catalyst and they are getting methyl isocyanate. And the non-green synthesis, they are using methanamine with carbonyl chloride. This is your phosgene, and phosgene is deadly poisonous. So you're using a poisonous material and you are again releasing toxic material. Acid is not at all environment friendly. So by using green synthesis, you can minimize the production of waste. Then the second principle which they're talking about, atom economy. Higher atom economy makes a process green. Now what is atom economy? So synthetic materials should be designed. Synthetic materials should be designed to maximize the incorporation of all molecules used in the final product. This is the concept of atom economy. So this means the atoms which are present in the reactants should be present in the product. Then only less amount of waste will be generated. So atom economy can be calculated using this formula: formula weight of atoms utilized by formula weight of all reactants. So you can say the formula weight of the product divided by formula weight of all reactants multiplied by 100. So this will give you the percent atom economy. Say, suppose for a particular chemical reaction, the atom economy is 50%. That means out of the total atoms present in the reactant, only 50% atoms are present in the product. Means the remaining 50% is waste, which we do not like to have it. So you have to design process as a new generation chemist. You have to design process where maximum number of atoms are incorporated in the product. Maximum number of atoms in the reactant are present in the product, then only the atom economy will increase. So here is a typical example. This is a 4+2 cycloaddition reaction, which you commonly call as the DLL reaction. So this is the diene, this is the dienophile, and you are hitting and you are getting a cyclohexane derivative. So here you see all the atoms of the reactant, they are present in the product. All atoms in the reactant are present in the product. That means atom economy is 100%. There is no single waste generated, and we can call it as a green reaction. So as I already told you, that prevention of waste and economy are the either side of a coin. When you generate less waste, your atom economy will become higher, and you can just call it as a green reaction. So earlier, before green chemistry took part, people tried to understand the efficiency of a reaction in terms of percent yield. Percent yield is the actual yield of the product divided by theoretical yield of the product into 100. This theoretical yield of the product can be calculated from the balanced stoichiometric equation. So it is the theoretical yield which can be calculated from the balanced chemical reaction from the stoichiometric coefficient, and the actual yield of the product is calculated after completing the reaction. But now the efficiency of a reaction is measured in terms of percentage of atom economy, which is the molecular weight of the product divided by molecular weight of all reactants multiplied by 100. So higher percentage of atom in starting material end up in final product, recycling material back into the process. Then there is another factor. Now we are trying to judge the greenery of a chemical reaction, that is the E factor, which is also called the environmental factor. So E factor is the total quantity of waste generated divided by quantity of product obtained. So definitely we'll like to have less quantity of waste, more quantity of product. That means a good green reaction will have low E factor. So we can measure the greenery of a reaction in terms of the atom economy or the E factor. So for a green reaction, there will be higher atomic economy and less E factor. So where does this waste generate? The waste generate from the auxiliary substances like the acids, the base, Lewis acids, then the oxidizing agents, sodium dichromate, potassium permanganate, manganese dioxide, reducing agent, lithium aluminum hydride, sodium boron hydride, etc. So let us try to understand some more example of reactions where there is 100% atom economy, and also chemical reactions where atom economy is very, very low. So this is an allyl phenyl ether, and you must be phenylallyl ether. So upon heating, you'll get orthoallyl phenyl, this allyl group migrates to the so this is a Claisen rearrangement. It migrates to the ortho position. So here also you'll see that there is no waste generated. So this is reaction where there is 100% atomic economy. Then this is a bromination of propene. So these are the reactant propene. The reactants are propene and bromine, and the product is 1,2-dibromopropane. And here there is no waste. There is no waste. That means all the atoms present in the reactant are present in the product. So this is a reaction which proceeds through 100% atom economy. Then again, the 4+2 cycloaddition reaction. This is the diene, this is the dienophile. On heating, you will get a cyclohexane derivative. Here again, there is no waste generated. So this is a reaction when there is 100% atom economy. And we wish that all the chemical reactions have 100% atomic economy. And then we can argue that we are generating no waste. So this is a green reaction. Now let us try to see this reaction. You are using ethyl propanoate with methanamine, and you are getting a substituted amide, and this is the byproduct. This is the byproduct. This byproduct, we wish it does not get produced. So this means all the atoms present in the reactant, all the atoms which are present in the reactant are not present in the product. This is only the product. This is the waste. So here, the atom economy will not be 100%. So this is the Claisen rearrangement, 100% atom economy. Now let us study an oxidation of alcohol using Jones reagent. So you already remember what is Jones reagent. It is a mixture of chromium oxide and 8 normal sulfuric acid. So Jones reagent basically is an in situ generation of chromic acid. So this is my reactant, this is the reactant, and you are getting this product, and see, you are getting lot of waste. You are getting lot of waste. So here the atom economy, this is the product you are getting. So you are getting 3 moles of product, and the total molecular weight of the product will be 360. And the total molecular weight of the reactant, if you calculate it, it will be 860. So the atom economy is only 42%. And when the atom economy gets lowered, the E factor increases, and the E factor is 1.5. So guess if the atomic economy is 100%, then E factor will be 0. Now they try to oxidize the same substrate using suitable catalyst. Here you see the waste generation is less, only the waste is water, and in fact water is non-toxic. And the atom economy has risen from 42% to 87%, and the E factor decreased from 1.5 to 0.1. So as tomorrow's chemist, you just remember, they will develop process, whether it is an addition reaction, whether it is an oxidation reaction, whether it is any synthetic reaction, that you try to develop the process where more atoms present in the reactant are present in the product, and which will increase the atom economy and decrease the environment factor. So this is again a classical route for the preparation of hydroquinone. So they are preparing from aniline. This is your aniline. First of all, they're oxidizing. They're oxidizing to give a hydroquinone. Then you are reducing it, and in the process, lot of waste are generated. These are the waste which are generated, and this waste we do not like to have it. And for this traditional route, for this classical route for preparation of hydroquinone, it is only 20% atomic economy. So they are using another process, and they are using catalyst, and they are using hydroquinone, and here the atom economy is 67%. So what I used to suggest, that green chemistry is a new phase of chemistry, and the chemists are trying to utilize these 12 principles, and they are trying to generate less amount of waste in order to increase the atom economy and decrease the E factor. So chromium 6, the chromium 6 is used as an oxidizing agent in the form of chromic acid. And they found that hexavalent chromium, highly toxic, highly carcinogenic, get into your DNA. So you pass the trouble to your kids. So today's lecture, I tried to elaborate the first two principles of green chemistry. That is the principle one, prevention of waste and atomic economy. And I hope you have enjoyed my lecture. And if you really like it, please share with your friends. And it will be immense help in the exam days. And also do not forget to subscribe my channel, Bedanta Borah Camps and Blog. So thank you. Have a nice day.